Hello, this is Professor Gavoor. I'd like to talk to you a little bit about demand planning and forecasting, and then give you some problems that have to do with that. Uh, Forecasting is a process of projecting the values of one or another variable into the future. Demand planning is a methodology companies use to integrate planning information from different departments or organizations into a single demand plan or forecast. A demand plan begins with a forecast. They call it a baseline statistical forecast, and then add company intelligence to it as they proceed. So forecasting is basically predicting the future, and people are not good at that. We like to believe we're wonderful at it, but you saw in the last election, the last two presidential elections, it was pretty hard to forecast who was going to win. There's a forecast planning horizon. We look at a variety of time buckets. You could forecast by day, you could forecast by year, you could forecast by month. You could forecast however you want. If you're the most common measure used in business in demand planning and sales forecasting, which is the most common form of forecasting. When people talk about forecasting in business, it's usually sales forecast. The most common unit of measure is a month. For manufacturing planning, your manufacturing plan could be a month, it could be a week, it could be a day, it could be an hour, or shift or an hour. Your planning horizon is over how many of these time units you want to forecast. Most people tend to forecast a few months ahead. A lot of consumer good companies will forecast a year in advance, the rolling year in advance. So right now, as I'm recording this, it's November 2020. People will be forecasting through November 2021. Walmart, when I last checked, was doing an 18-month rolling forecast. They forecast by the month every product that they sell, and they would forecast in this month of November. They would be preparing a forecast for December 2020, which is probably the most important month. But that month is probably already well planned. They would probably be looking at really trying to solidify February 2021 through November. Then they would forecast through November 2021, of course. But then if it's 18 months, they would do 6 more months. So that would be December, January, February, March, April, May of the following year, 2022. There are all kinds of data patterns that we look at when we want to see this. Well, certainly we look at trend. We look at, most forecasting, the kind that I'm talking about, sales forecasting, the x-axis is always time. That's where we establish a time unit, month, year, day, however we want to look at it. So the independent variable, or the x variable, is time. Hence, the y variables, which are sales, it could be units, it could be in dollars, is called a time series because the x-axis is always time. Well, there's a few patterns we want to look for. We want to look for trends. Are my sales going up? I would be very happy with that. Are my sales going down? Are they trending up or trending down? And if they're trending up or trending down, what pattern is the trend? Is it linear? Is it parabolic? Is it exponential? Is it logarithmic, trending up and down? Then you have seasonal patterns. Some products sell better in the summer and worse in the colder months. Some products sell better in the colder months and worse in the warmer months. Those are seasonal trends. Then you could look at cyclical patterns. These are regular patterns in a data series that take place over long periods of time. The best example I could give you for that is when I first started working in the auto industry seemed to have a 5-year cycle. If you had a boom year in year one, somewhere around year 3, you would have a down year. Year 2 would be a little bit less than the boom year. Year 3 would be the pits, maybe year 4, and then year 5 would come around, and then year 6 would be kind of the same as year 1. There's random variation, there's unexplained deviation of time series from a predictable pattern. And then there's irregular variation, one-time variation that's explainable. The stock split, the company was bought, the CEO was arrested for fraud, and the CFO for fraud, makes the stock tank. So random variation is that day-to-day variation when you look at a graph of stock day by day. There's zigs and zags a little bit. You can see, if you stand back and squint your eyes, you can see a trend. But when you open your eyes and get close, you see these little zigs and zags. Those are random variation. If the stock is stable at 100, your random variation could be the next day it's 100 and it's $100.10. The next day it's $99.50. The next day it's $100.42, and et cetera, like that. So it hasn't. The average tends to be the same, but there's just variation in the stocks. Here's an example of linear and nonlinear trends. I would say linear increasing, decreasing trend. You have a time on the x-axis again, the volume either in dollars or units, and you see that the trend is heading downwards. If these are, I'm trying to predict sales, I'm not happy, my sales are going down, what's going on, what's wrong? If I'm doing a linear increasing trend, I'm a much happier person because I see the trend going up. This is a nonlinear trend, and this looks like exponential growth. This looks like logarithmic decline, nonlinear decreasing trend. This is kind of how salespeople always look at the world. Things seem relatively flat, and you are right here. This is the time you're at. What's the forecast? Salespeople are very, very optimistic. They always think they're on the brink of something like this. They're always here. Some people call it a hockey stick because it's linear until, it's flat. Sales are flat. But then it's going to take off like this. So then it takes off in a linear direction up here. So here's the flat part of the hockey stick, and you're always at this corner. And salespeople, well, you pay salespeople to be optimistic. You want them to be optimistic and have really cool, broad forecasts like this. And here, sales are very good, and then you're about to fall off a cliff. Here's one that shows a cyclic pattern. Natural gas usage doesn't change that much, so the linear trend is probably flat. But you look at it, and if we're talking about Chicago or the northern countries, boy, in January you use a lot of natural gas to heat your house. But then as the months get warmer, you use less and less natural gas. It doesn't go to zero because people cook also with natural gas. Heat water, the water heaters in our house use natural gas. But then starting in September, when the weather starts to cool off, the usage goes up dramatically into January, and then begins a downward trend again to the summer months. So this is a cyclical pattern, a seasonal pattern. Now, if it was lawnmowers, you would be selling no lawnmowers in January, but it would increase the opposite way. It would increase in the summer months and then go down in the winter months and go up and down. If I did snow shovels, it would be like this. If I did winter hats, winter clothes, it would look like this. If I look like summer clothes, it would have much like the lawnmowers. It would peak here and valley here. and peak here and valley here. How do we estimate forecast error? Well, there's three ways. There's the statistician's way, which really it used to be the only way we measured it. But it was not a good way because, well, it's hard to interpret it. It's like standard deviation. It's a great measure of dispersion, but it's an awful measure to try to fathom, if you will. We know how, in a normal distribution, how important the standard deviation is. So we use standard deviation all the time. So all forecasting is based on errors. Actual minus forecast. Actual minus forecast. Actual minus forecast. The little t is the time period. You want the actual in time in the month of March minus the forecast in the month of March. So that would be A3 minus F3. Or actual of 3/20, which would be March 2020, minus a forecast in 3/2020. But if I add up and take the average of my errors, if I forecast properly, half the time I'm going to be forecasting a little bit high, sometimes I'm going to be forecasting a little bit low. And if I just add up the errors, they tend to come out to be very close to zero. So the way statisticians measure this kind of variation is they don't take the absolute value like we're going to do in the second example. They square it and then take the average. The capital T is the number of time periods over which you sum these errors. So mean squared error is almost like the standard deviation. It's actual minus forecast for each corresponding period, square them, add them up, divide by the total number of time periods that you looked at, mean squared error. It's influenced by large forecast errors, more than small forecast errors. I'm not sure I agree with that, but it's a hard measure to interpret. A better measure, since errors add up to zero, why don't I just look at it and say, why don't I take the absolute value of this? I don't care if my forecast is high or low, really. If they're all high, I have a bias. So I have to get rid of the bias. If they're all my forecast, if the actual is always higher than a forecast, I'm forecasting too low. So I have a bias to forecast on the low side. So I want to fix that bias. So you want to look at these and see if they're mostly negative or mostly positive. But for my accuracy, I want to take the absolute value of them, which means strip them of negative signs, and then take the average of that deviation. So it's the mean is average, absolute for absolute value, deviation is this forecast error, and it's called mean absolute deviation, or MAD, mean squared error is MSE. This one makes a lot more sense. How much am I off by if I'm selling cars? Was I off by 10 cars on the basis of a couple hundred cars, or was I off by 10 cars on the basis of selling 50 cars? It would make a difference. Can I live with that kind of error? Is it accurate enough for me to live with? Well, most people take it one step further these days. They look at mean absolute percent error. So mean absolute error, they take the actual minus forecast for a time period, take the absolute value of it, but they divide it then by the actual for that same time period and multiply it. So how much is the forecast, how much was my error as a percentage of the forecast, multiply it by 100, and then take the average of those. So measurement scale factor in mean absolute percent error. Each one of these terms for a particular month, let's say April, the actual in April minus forecast in April divided by the forecast or the actual in April times 100 is called average percent error. That's an APE. It's not until I average them all that I get the mean absolute percent error, the MAPE. And people do call it MAPE. This is probably the most popular forecast accuracy measure that is used today in industry. So statistical forecasting is based on the assumption that all the future will be an extrapolation of the past. What does that mean? The immediate future will act like the immediate past is what we're saying. And there's two ways of doing it. There's using time series methods, which extrapolates historical time series data. And then we can use linear regression. You remember that from your stat class. That extrapolates historical time series data and includes other potentially causal factors that influence the behavior of the time series. We're going to look at only 3 methods, and then we're going to actually show you put them in place, because these slides are not going to give you the answer or the methodology that you want to use. So moving average forecast. It takes the most recent K observations of a time series, the one that you actually have the actuals for, and it just averages them and says that's going to be my next forecast. So it's a smoothing method. Averaging tends to smooth things out. So moving average methods work best for short planning horizons when there's no major trend, seasonal, or cyclical business pattern. Well, there could be some trend, but it's going to smooth it out and it's going to lag behind it, is what they're telling you. As the value of K increases, the forecast reacts slowly to recent changes in time series. The most popular versions of this for K, the most recent K observations, are 2, 3, 4, and 5. And mostly 2, 3, and 4. And most of the time in most textbooks, they use a 3-month moving average. And we'll show you an example. The other one is exponential smoothing. They use a weighted average of the past time series value to forecast the value of the time series in the next period. So the forecast in the period t plus 1, let's say we're at time t now. We just finished October. T is October. We want to forecast November. So I pick an alpha between 0 and 1, and I say I'm going to take my actual times alpha plus 1 minus alpha times a forecast. So it's taking an average of the actual and the forecast. And if you do the math here and simplify it, it's really the forecast for the next month is the current month forecast plus and what is this? Actual minus forecast. That's the error. And notice there's no absolute value, so it would be plus or minus. And you multiply that by alpha. So alpha is called the smoothing constant. You have to try this to actually see how it works. Our regression analysis. We're going to use simple linear regression. In this case, the forecast Y. We have a single dependent variable and one or more independent variables, but most of the time we're going to use one independent variable here. So simple linear regression means find the best values of A and B using the method of least squares. Excel provides a tool to find the best fitting regression model for a time series by selecting and adding trend line options. You can make it logarithmic, you can make it exponential, you can make it polynomial, you can make it a power curve or moving average. So Excel does help you there. So causal forecasting with multiple regression. Multiple linear regression has more than one independent variable. You could have other independent variables that influence the time series or economic indices, demographic factors, the consumer consumer price index. It could be inflation rate. It could be unemployment rate, because if you're trying to forecast sales in a department store or something, or an online store of some sort, your sales could be dependent on what the unemployment rate is. So I would have my time series, my month. I would have the inflation rate and maybe the unemployment rate, and then use those factors to try to predict sales. Then there's a mess of other stuff that people use when you want to take a baseline statistical forecast. And let me say one other thing about regression. If I use the previous actuals in my forecast, or I lag them by a month, that's called auto-regression. We're not going to cover that, but it's also a very popular model. The problems with exponential smoothing and simple moving average is it only forecasts the next time period. Well, if you're Walmart and want to forecast 18 months out, that's an issue, because these things only forecast 1 month out. Regression can forecast your trend out infinitely. But the problem with regression is you've committed to a line, you've committed to a trend. If B is positive, your data is always going up. If B is negative, your data is always going down. We talked about that. Now, the way you take a baseline statistical forecast, just using past data to predict the future, is you use all kinds of methods of tapping into your salespeople, your marketing people, your corporate economists, and getting their information and asking them for what they think, what knowledge they know that may make the forecast that would make you want to adjust the forecast either up or down by some amount. So this idea of grassroots forecasting, asking those who are close to the end customer about the customer's purchase plan. Those are your salespeople. The Delphi method, forecasting by expert opinion by gathering judgments. I'm sure they adjust the presidential forecast using some sort of Delphi method. Forecasting in practice. Managers use a variety of judgmental and qualitative forecasting techniques. In fact, one thing that I'm pretty certain that's very flexible and it has the best of exponential smoothing and regression is called the Holt-Winters method. And it is not limited to just forecasting the next time period. You can project out much further. So it takes into advantage cyclical trends. It takes into advantage seasonality, and it takes into account any positive or negative trends happening. And if your trend goes up and then starts coming down, it will kind of react to that. So statistical forecasts are adjusted to account for a variety of qualitative factors. Like we just said, using grassroots forecasting involving experts in your company. If you know that you're selling to Target and Target's going to open 50 stores next month, which is a huge number, how does that work? If you know you're selling to one of those department stores that is about to declare bankruptcy, you'd like to not use their historical data to forecast what you think they're going to buy in the next few months, because they're probably not going to buy that much, if any at all. So there's another thing called a tracking signal. Provides a method for monitoring forecasts by quantifying bias. Now, this is the deviation. This is the error. The actual for a given month minus the forecast for a given month. It could be positive or negative. You divide it by the mean absolute deviation. So now And when you take that and sum that up over all the time, if that's a negative number, you're under forecasting. If it's a positive number, you're over forecasting. If it's close to zero, you're probably happy. Tracking signals between plus and minus 4 indicate an adequate, safe forecasting model. Now, everybody wants their MAPE, mean absolute percent error, to be really close to zero. Oh, we love that. But to be honest with you, plus or minus 30 in consumer goods is considered okay. I mean, you want to do better than that, but there's variation in the sales, and you can't dampen the variation, the random variation. So the more variation there is, and you can measure that as the ratio of standard deviation to mean, the higher that is, S divided by X bar, the higher that is, the harder it will be for you to accurately forecast. So forecasting is a science, it's also an art. So the process of projecting the values of one or more variables into the future is known as forecasting. Statistical forecasting and regression analysis are the methods used for forecasting. So thank you for listening. If you have any questions, if this was a live lecture, you could ask me. If it's a video lecture, you have to email me. Thank you so much.